Okay, team. In this next section, we're going to talk about how to interpret an ABG. ABG stands for arterial blood gas. Now, you can have a VBG, or a venous blood gas, coming from a venous source. However, it is not as reliable as an ABG, and your reference ranges here would be different. So, standard of care really is to use an ABG. ABGs can either be written out, such as this, or in their abbreviated form with the slashes in between, such as this. You can have abbreviated forms of your CBC and BMP similarly. If you guys ever end up on an ICU rotation or an internal medicine rotation, you'll see this happen a lot. So let's talk about the components of the ABG. So the first thing you have is the pH. This is the pH of your blood. Normal pH is about 7.4, with about a 0.5 differentiation each way, meaning that normal ranges between 7.35 to 7.45. If it is less than the 7.35, that is a sign of an acidosis or an acidemia. If it's higher than this is an alkalosis or an alkalemia. Next, you have your PaCO2. This is your partial pressure of carbon dioxide. As we've mentioned before, carbon dioxide overall acts as an acid in the system in a way, where if you have a higher amount of it, it causes an acidosis, or it can cause an acidosis, but overall makes the system more acidic, versus if it's lower, it's more alkalosis or alkalytic. PaO2 is important as far as trying to make sure that we maintain a regular oxygenation of the blood. However, for our purposes today, and whenever we talk about ABGs, it's not quite as important. And then finally, we have bicarbonate. Bicarbonate ranges between 22 to 26. You will see that sometimes it's 22 to 28, such as what you see in the BMP here. You'll also notice that bicarbonate does get tested in the ABG and the BMP. It's thought that the BMP is more specific. However, whenever you think about timing-wise, usually you'll use your ABG together. So unless you get a BMP at the exact same time as you get an ABG, you can go ahead and use your bicarbonate that's in the ABG to help determine your acid base. So bicarbonate, if it is low, that means that you're being more acidic. If it's high, that's more alkalosis. Now, as we mentioned in the previous section, CO2 is primarily regulated by the respiratory system. Bicarbonate is primarily regulated by the renal system. Whenever the primary disturbance is a PaCO2 problem, it's usually known as a respiratory, versus if it is primarily a bicarbonate problem, it is known as a metabolic. So whenever we think about metabolic versus respiratory acidosis and alkalosis, this is what you're going to be thinking about, whether or not the primary problem is the bicarbonate or the primary problem is the CO2. So when you're interpreting an ABG, it takes 4 steps if you want to determine the compensatory response. First, you want to categorize the pH. If it is low, it's an acidosis or an acidemia. If it is high, it's an alkalosis or an alkalemia. If it's within the normal range, you can call this normal, or in some cases, it can be compensated. Remember, our body does not want to be in an acidic environment or too basic environment. So if you do have a problem where you have a low CO2, for example, it is quite common that it's also going to decrease your bicarbonate because you're trying to compensate. If your body's able to maintain a normal pH, it would be a normal or compensated acid-base disorder. If it was that your CO2 got so low that it actually affected your pH, then that's whenever you consider an acidosis. So next you classify your bicarbonate. Your PaCO2. You want to know whether or not it is high or low. As you're doing this, you're going to start thinking to yourself, does this PaCO2 being high make sense in the context of an acidosis, or does it make sense in the context of an alkalosis? Similarly, you'll do the same thing with your bicarbonate. Using these two things, you're going to help determine whether or not you have a respiratory problem or a metabolic problem. If you have an acidosis and you have a high, so pH is low, and a high CO2, this would be a respiratory acidosis, meaning that the primary problem is that you have a low pH, that's why it's an acidosis, and that your CO2 is high. We're going to talk about this more on the next slide, but CO2 acts as an acid, so this would be the primary problem. Again, we'll talk about it more on these next couple slides, but just start thinking to yourself, is it a metabolic problem or a respiratory problem? If it is a metabolic acidosis, you do need to calculate an anion gap. Anion gap is calculated, this is also known as serum anion gap, so SAG, and it's calculated as your sodium minus your chloride minus your bicarbonate. Sometimes we'll say pluses minus minuses because sodium is a cation and chloride and bicarbonate are anions. This fourth step is an optional step for you guys, but one thing you can do is determine the compensatory response and whether or not there is a compensation going on. This is provided, there are tables provided in your DePiro's book with these calculations, but you can do calculations to help determine whether or not you have a compensatory response. So when you're analyzing the ABG, it's pretty easy to tell whether or not you have an acidosis or an alkalosis, because you'll just look and see, is my pH high or low? If my pH is high, alkalosis. If my pH is low, acidosis. When we are looking for whether or not it's a respiratory or metabolic cause, this takes a little bit more thought. So remember, and I know I keep saying this, CO2 acts as an acid. So if you have a high amount, if you see that you have a low pH, and then you look next door and you see that you have a high CO2, that would make, I start thinking to myself, does this make sense? Because if I have a low pH and a high CO2, CO2 is acting as an acid, thus this could be what's driving my pH down, then I can start thinking it's a respiratory acidosis. Now what you're going to find as you go further down, after you mark out your O2, is that you're going to find that you have a high bicarbonate. This is the compensatory response. Remember, our body does not want to be outside the normal range in pH. So as we're trapping more and more CO2 or having higher CO2 levels, our kidneys are trying to get as much bicarbonate into the system to try to make sure that we maintain a normal pH. However, in these respiratory acidoses, that CO2 has overcome the amount of bicarbonate to cause you to have a low pH. So you're going to have to think about this and really start thinking about what you think the primary disturbance is. If you have a metabolic acidosis, you would see that you have a low pH. And then whenever you look next door at your PaCO2, whenever we're talking about with the abbreviated ABG, you'll see that that's low. You'll think to yourself, well, my pH is low. CO2 acts as an acid. Why would I have a low CO2? That's whenever you have to go down further and look at your bicarbonate. Your bicarbonate, in that case, would also probably be low. Having a low pH and a low bicarbonate together tells us that it's a metabolic acidosis. The exact opposite occurs in respiratory alkaloses and acidoses. Respiratory alkaloses and metabolic alkaloses, with your pH being high, your PaCO2 being low. So you'd look next door and be like, okay, low PaCO2, high pH, that makes sense. Must be a respiratory problem. And then you'll see the compensation is having a low bicarbonate because CO2 is acting as an acid. Acting as a base. Well, it's acting as an acid, it's being low. So you're trying to get rid of all the excess base in the system to try to overcome it, so that's your compensation. Similarly, in a metabolic alkalosis, you're going to have a high pH with a high bicarbonate. So you have excess base in the system. In order to overcome this excess base in the system, your lungs get the signal to try to increase the amount of CO2. It gets overcome, so you have a metabolic alkalosis. One really easy way just to do this, and like this is kind of what I call a quick and dirty trick, is remember, or think about it this way. Same, SAME. The last two letters are ME. The first two letters of metabolic are also ME. When you look across these disturbances, and even whenever we do our examples, you're going to see these arrows are all going the same way. If your pH is low, and then both your PaCO2 and bicarbonate is low, it kind of tells you that it's a metabolic problem. Similarly, if you see that all these are high, also tells you a metabolic problem. Metabolic problems typically go in the same way. Here's the same ABG analysis with the numbers in there, just for your reference. And if you're more of a flowchart girl like I am, you'll see that this is also helpful. What you would do is you would look at your pH. If you have an acidemia with a high PaCO2, it's a respiratory acidosis. If you have an acidemia with a low bicarbonate, it's a metabolic acidosis. Opposite on this opposite side with alkalemia. And then if it's within the normal range, it can be compensatory or mixed, but you can just call it normal for our purposes. If you do see, such as on an exam, that you have a normal range here, you can just state it's normal. I think the best thing we can do here is try to do some examples. So let's just remind ourselves of what the steps are. Number one, we want to categorize our pH. Next, we want to categorize our PaCO2. 3, categorize our bicarbonate. That's 3A, 3B. Determine if it's respiratory or metabolic. If a metabolic acidosis, then calculate serum anion gap, and then 4, compensation. For our sake, today we're not going to talk about we're not going to really calculate the compensatory response. So let's do this. First, categorize the pH. So in this first problem, is our pH high or low? Hopefully you guys are just talking to yourself like it's Dora the Explorer and you say low. So that's a low pH. We look next door at the PaCO2. Is that high or low? High PaCO2. We can just mark out this PaO2 because it's not that important for us today. And then finally, your bicarbonate. Is your bicarbonate high or low? High. So, next let's think about if it's respiratory or metabolic. You have a low pH and a high PaCO2. PaCO2 acts as an acid, so if that's high in the context of a low pH, this must be a respiratory problem, because that makes sense. Having high bicarbonate with a low pH, though the compensatory response obviously is not the driving or primary disturbance, because it's not the thing that's decreasing your pH. So another way you can do this, and I'll show you it this way. So first you look at your pH. Is it high or low? Hopefully you guys are all saying low. So you can automatically write down acidosis. Next we look at our PaCO2. High or low? Low. Don't really care about our O2 today. Third step, looking at your bicarbonate. Is it high or low? Low. So we start with our pH. So we already know it's an acidosis, so now we just have to know if we need to write down respiratory or metabolic. So we start with our pH, looking next door at PaCO2. Does that make sense? If you have a low pH and having a low PaCO2, is that your primary disturbance? No, because this low PaCO2 should be increasing. your pH. So then we go from pH to the bicarbonate. Do those two make sense together? Yes, because bicarbonate's a base, having low base in an acidic environment. Those two things would be together. So that's the primary problem. This PaCO2 is just your compensation. So this would be a metabolic. And remember, the same mnemonic, so the ME, all of these arrows are going down, tells you it's metabolic. Versus in this respiratory problem, you see my arrows going down, up, up. Let's do this next one. pH is high. PaCO2 is low. Bicarbonate is low. See that it has a high pH, so we already know this is an alkalosis. Low PaCO2 with a high pH does make sense together. The CO2 is acting as an acid, having low acid in a basic environment. Makes sense. Having this low bicarbonate is obviously the compensatory mechanism because that's going in the opposite way. So this is a respiratory alkalosis. pH, high. PaCO2, high. Don't really care about O2. And then your bicarbonate is also high. All these are going the same way. So we see that the pH is high, so we already know that this is an alkalosis. All these are going the same way. So ME, metabolic. And again, if we do this, try to think through it, you see that having a high pH and then also having a lot of acidic carbon dioxide in the system don't really go together because this is a compensatory mechanism. So then we go down to our bicarbonate. The bicarbonate is high and the pH is high. So obviously we're in a basic system with a lot of base. This is a metabolic problem. So let's do some examples of calculating an anion gap now. So again, the only time we have to calculate an anion gap is if it's a metabolic acidosis. And in the next section, we're going to talk about metabolic acidoses. So anion gaps are simply, so SAG standing for serum anion gap equals concentration of sodium minus chloride minus bicarbonate. Again, pluses minus minuses. So 140 minus chloride's 100 minus bicarbonate's 25. Your serum anion gap is 15. Let's do this one. Sodium is 145. Chloride is 97. Bicarbonate is 23. That's going to equal 25. We're going to talk about what the normal range is and why these are important in the next section, but I want to make sure you guys know how to calculate them.